E is irrational. Here's why. So one of the definition of E is just E is equal to the limit of n approaches infinity of 1 plus 1 plus half plus 3 factorial 1 over 3 factorial plus all the way up to 1 over n factorial. Now let's look at the finite sum of Sn equal 1 plus 1 plus half plus 1 over 3 factorial plus all the way up to 1 over n factorial. N is a finite positive integer where S sub n plus m is equal to 1 plus 1 plus half plus 1 over 3 factorial plus all the way up to 1 over n factorial plus 1 over n plus 1 factorial. Right, keep going. Plus all the way up to 1 plus n plus m factorial. And what's the difference? The difference, so I want to have a look at S sub n plus m minus S sub n. Right? So it's obvious that we can cancel out the majority of the terms, right? Namely the first, right, those terms, right? Those terms. We're only left with the remaining. So what is that? That is equal to 1 over n plus 1 factorial plus 1 over n plus 2 factorial all the way up to 1 over n plus m factorial. Right? So we can just simply extract 1 over n plus 1 factorial, and that is equal to 1 over n plus 1 factorial quantity 1 plus, what do we have left? 1 over n plus 2. Right, what's next? 1 over, only left, the next one is 1 over n plus 3 factorial after extracting 1 n plus 1 factorial. We're left with just n plus 2 times n plus 3, right? All the way up to, what do we have left here? We have 1 over, likewise, n plus 2 times all the way up to n plus m, right? Quantity. Then we can simply just loosen the inequality a little bit appropriately. Right? So that is we can loosen it. I say this is no larger than strictly less than, copy it down, 1 over n plus 1 factorial times quantity. I'll keep the 1. And plus I will replace n plus 2 with n plus 1. And I will replace n plus 2 and n plus 3 with n plus 1 and n plus 1. So I have 1 over n plus 1 squared. Likewise, I will replace every term with n plus 1. Right, next I have 1 over n plus 1 cubed. All the way up to 1 over n plus 1 to the power of m minus 1. m minus 1, right? This is what I have, m minus 1. Here we have 1 over n plus 1 factorial. And here we have a geometric sequence, obviously. Right? The first, so what's the common ratio, 1 over n plus 1. Right, so we have 1 minus 1 over n plus 1. Right? On the top, we have first term is 1, right? So we're fine. So 1 minus common ratio to the power of how many terms do we have? Exactly m terms. Right? And of course, that is no larger than if we just get rid of the minus 1 over n plus 1 to the power of m, right? Because originally we subtract some positive number. Now we don't subtract it. Now we are bigger, right? So 1 over n plus 1 factorial times just 1 over this, right? So 1 over this common denominator, n plus 1, we have n plus 1 minus 1, n over n plus 1, right? Reciprocal, we have n plus 1 over n. Right? Then n plus 1, n plus 1 factorial, simplify down to n factorial, and we have n. So we have 1 over n factorial times n. Right? So that way you can see that our estimation has nothing to do with m anymore, right? It's only an expression involving n. Right? So that means this inequality is true for any m, right? If we let m approach infinity, it still remains true, right? I let m approach positive infinity, inequality still maintains. Right? So what happens when m approaches infinity? So what happens is that s sub n plus m, n is fixed, m approaches infinity. So the whole subscript still approaches infinity, right? So that is exactly the definition of E, right? So therefore we have E minus S sub n is no larger than, maybe we can, after we take the limit, we will just add equal sign, right? No larger than 1 over n factorial times n. And we also know that Sn keeps increasing, monotonically increasing, right? Monotonically increasingly approaching E. So therefore it is definitely no larger than E, right? So therefore E minus Sn has to be positive. So now I've established the following fact, that E minus S sub n is positive, first of all. Then it is no larger than 1 over n factorial times n. So what if we let n equal to 1, right? So we have 0 is less than E minus, what is S sub 1? Right? S sub 2 is 1 plus 1 plus half. So S1 is 1 plus 1, that is 2, right? Minus 2. No larger than 1 over 1, right? So first of all, E is bigger than 2, strictly bigger than 2, and less than or equal to 3. Right? What if we let n equal to 2, right? This time, what will happen? So that is, we have E minus S sub 2. S sub 2 is 1 plus 1 plus half, 2.5. Right? Is no larger than 1 over 2 factorial times 2. 1 over 4. 0.25, right? So that means we have the following fact, that E is not only strictly bigger than 2, but strictly less than 2.75, which is strictly less than 3, right? E is really strictly between 2 and 3. So which means E cannot be an integer. So we will prove by contradiction prove by contradiction. We will assume that somehow E is rational, equal to P over Q, where P and Q are both positive integers. Prime, co-prime or not, doesn't matter. So, in this case, we can simply let n equal to q. I see what happens. First of all, I know that q cannot be 1. It must be strictly bigger than 1, because if it were 1, then we have an integer. Right? So I know that q is strictly bigger than 1. So in other words, q, when n equal q, we still have this inequality, right? So 0 is less than e. E is assumed to be p over q. So p over q minus sq. Right, sq, what is sq? Sq, 1 plus 1 plus half plus all the way to 1 over q factorial, right, is no larger than 1 over q factorial times q. Right. So what if we multiply by q factorial on both sides? We still have 0 is strictly less than, what does p over q times q factorial, right? Simplify it down to q minus 1 factorial times p. Right? Of course, this is integer. And minus still times q factorial, right? 1 plus 1 plus half plus 1 over 3 factorial times all the way up to 1 over q factorial less than or equal to 1 over q, or q factorial cancel out. Like I said, q is strictly bigger than 1. Therefore, 1 over q is strictly less than 1. Right? It can either, could be 1 over 2, 1 over 3, 1 over whatever. It is strictly less than 1. Now, so what do we have in the middle is some number that's strictly between 0 and 1. So meaning it cannot be an integer, right? It cannot be an integer, right? Cannot be an integer. But q is an integer, right? Positive integer. So therefore, q minus 1 is a non-negative integer. Right? So non-negative integer factorial is at least an integer, right? Positive integer, 0 factorial, still integer. 1 factorial, 2 factorial, still integers. Integer times p, an integer, right? Still an integer, right? Integer is closed, you know, in terms of operation, time, multiplication, addition, right? And q factorial integer times, right, distribute onto each and every one of them, right? So we have q factorial times 1, q factorial times 1, q factorial times 1 over 2 factorial. As long as the denominator, right, whatever factorial, as long as this number is less than q, we can always simplify it down to some integer as well. Right? For example, q was 5. If it's 1 over 4 factorial, right, then we have 5 factorial over 4 factorial. Right? We can always have an integer. Right? Because 5 factorial is 5 times 4 factorial. 4 factorial times 4 factorial cancel out. Right? Always an integer until we reach 1 over q factorial. Right? Still an integer, right? 1. Right? So in the end, this is always some integer. Right? So we have integer minus integer, still an integer, right? Still an integer. So that's a contradiction, right? Like I said previously, we've shown this number is some number strictly between 0 and 1. So meaning it has to be a strictly decimal number, right? Cannot be an integer. But now we've shown that, right, it's an integer, because integer is closed under addition, subtraction, multiplication, right? Closed. So an integer, so contradiction. So that means my assumption is false. So E is irrational.